Dear academicians and researchers, ladies and gentlemen, I am Artem Chamili, and it's my pleasure to be part of the third International Conference on Science and Engineering, where I'm going to present a joint paper of a few authors entitled Secure Naïve Bayes Classification Without Loss of Accuracy with Application to Breast Cancer Prediction. This is the content of our paper of the talk that I'll be giving today. And let's start with the preliminaries or the scope of the problem. Namely, we deal with a scenario where we have a server which has an already trained machine learning model and a client or a user which has a query, unclassified query vector, and this client wants to classify his or her query using the server's trained model. However, they want to do it in privacy-preserving fashion. Namely, from the server perspective, we don't want any information of the trained model to be leaked, whereas from the user's or client's perspective, we don't want any query or classification information to be leaked out. So those are our main goals. Of course, among them, we have other security, privacy, as well as some computation and communication efficiency goals, which can be read from the paper. Now, let's start with our preliminaries. So we are going to train Naïve Bayes model using a certain dataset. That dataset has F features, C classes, and NT number of transactions of records or instances or raws. So those features, F features, are basically grouped into sets of F features denoted from F1 to FF, or with index Fi, where I is the index that we are going to use throughout this talk and the paper, with which we are going to denote the feature sets. So ith feature set is denoted as Fi, and it's basically a set of values that it can take. So basically, the ith feature, the values that Fi feature offers are value 1 of feature Fy, value 2 of feature Fi, and so on up until value Fi of feature Fi. Well, this notation here represents a number of elements for the cardinality of the set Fi. Similarly, for the C classes, we have a set of C elements denoted as C1 through CC. And we are going to use variable K to iterate or go through the classes. So basically, K can take the values from 1 to C. Now, with this notation and CK, we denote the number of records or rows in the dataset that belong or are liable to belong to class CK. Furthermore, with this notation over here, we denote the number of records or rows which are liable to belong to class CK, and furthermore, for the ith feature, they have its jth value. Furthermore, we are going to denote the class probabilities as the number of records belonging to a certain class divided by the number of transactions. So class probability of CK is equal to the number of records belonging to the class CK divided by the number of transactions in our data set. And we are going to denote the conditional class and feature value probability as the number of records in our data set which are liable to belong to class CK, but in the corresponding field of feature Fi, they have the jth value divided by the number of records in our dataset belonging to class CK, where in this case, I goes from 1 to F, J is basically the cardinality of the feature values that we're going to use for each of the feature class. It goes from 1 to Fi, the number of elements of Fi, and I is again this index over here, and K is going to be used to iterate through classes, so basically it goes from 1 to C. If we have all of those probabilities for each class, and all of the conditional probabilities for each class and each feature value of each feature, then we have the trained Naïve Bayes model. Now, if we have an unclassified query, which is denoted as X, and is basically a vector which has F entries, denoted as x1 through xf, where xi is an element of fi. So basically, ith entry of this query over here can take only one value of feature fi. Then we're going to use this formula to label this query vector as to belong to a certain class from the set of classes. So basically, this is what the formula says. The label of this feature vector, query vector, feature vector x, is going to be the maximum of the posterior probabilities when we observe this query vector x and the probability of it to belong to class ck. So if we observe this vector x over here, there is a certain probability for it to belong to any of those classes, and we want to find the maximum of it. This is what the formula is saying. Now, if we use the Bayesian formula, this term over here can be expressed in this way, but since we don't care about the exact values of the class probabilities of the posterior probabilities, then we can just remove this term because it's equal for all of the classes. Furthermore, we naively assume that those features over here of the query vector are independent of each other. That's why this term over here can be expressed with this formula over here. With this formula over here, and when we put everything in the original formula, then this is what we get. Basically, the label of the classification of our vector x is going to be the maximum posterior probability of those terms. So basically, we are going to find those terms for each of the C classes, and we are going to assign the label to query vector x, which has the highest value, which basically means it has the higher posterior probability, which means that has the higher probability of this vector when we observe this vector x for it to belong to any of those C classes. So we select just the highest of them, the maximum of them. Okay, so far so good. Now let's continue with other preliminaries. Homomorphic encryption. Homomorphic encryption is a public key encryption system, so basically, which allows us to do some operations on the ciphertext while they are not encrypted, while they are still encrypted and without decrypting them. So this is called homomorphic encryption, and the operations that we do to the ciphertext when they are encrypted are called homomorphic encryptions. Namely, if we have an encryption of 4 and 7, we are going to have those ciphertexts. If we add those ciphertexts, we are going to get another ciphertext. Okay, so we do the operations while they are still in the ciphertext, still encrypted. And if we decrypt this ciphertext, we get 11. But hey, 4 plus 7 is 11. So we can do additions on the ciphertext. Furthermore, if we just encrypt 4 and 7 again, and we get those ciphertexts, and we multiply them, we're going to get another ciphertext. And if we decrypt the multiplication of those two ciphertexts, we're going to get 28. Hey, 4 multiplied by 7 is 28. So this is called homomorphic encryption, or somewhat homomorphic encryption, which allows us to do additions and multiplications on the ciphertext without decrypting them. But as we're going to see, the number of multiplications, it's kind of in somewhat homomorphic encryption schemes is somewhat limited. So it's going to be explained better in the next slide. So somewhat public key crypto systems are basically based on the hardness of ring LWE, and they allow 2 homomorphic operations on the ciphertext, which we saw, and their addition and multiplication. The number of homomorphic operations, especially of multiplications that we can do one after another without decrypting the ciphertext, is called the depth of the circuit. And here the plaintext, and this is the interesting part, the plaintext and the ciphertext of those somewhat homomorphic public key crypto systems are basically polynomial rings with modulus x to the power of n plus 1. and their coefficients are integers modulo t and q, respectively, such that this q is much greater than t. So basically, the plain text ring is this one. Okay, it's a polynomial with this modulus x to the n plus 1, and coefficients of this polynomial are modulo t, while the ciphertexts are polynomials, again, with modulus x to the power of n plus 1, and the coefficients of these polynomials are modulo q. Again, q is much greater than t. Now, if n, t, and q are chosen properly, then we can apply the Chinese remainder theorem, which basically enables us component or index-wise homomorphic SIMD operations of the polynomial coefficients. SIMD stands for single instruction multiple data. It's better expressed in this figure over here. So basically, if we have a ciphertext A and we have encrypted here, you see n integers, okay, because this is mod x to the power of n plus 1. Basically, we can have n coefficients. And integers, and all coefficients, by the way, are integers, both for the plaintext and the ciphertext. And if we have two ciphertexts, AC and BC, if we add those ciphertexts in the way that we saw previously, but if we have done it using the Chinese remainder theorem, then what we get is basically in parallel, as we have if we had index-wise or component-wise all of the elements. So basically, 5 plus 2 is 7, 8 plus 1 is 9, 3 plus 4 is 7, etc. And here n is usually thousands of coefficients, basically 4,000, 16, 32,000. We do it with one homomorphic operations. We are adding thousands of integers. Similarly, we can do the same with multiplication. So again, we have AC and BC. Basically, they are both the same ciphertexts. If we multiply them with just one multiplication using single instruction multiple data, this is what we have: index component-wise multiplications. So 5 multiplied by 2 is 10, 8 multiplied by 1 is 8, 3 multiplied by 4 is 12, and so on. Furthermore, not only additions and multiplications, we can do rotations of the coefficients inside of a ciphertext. So here is shown a rotation to the right. Basically, all of the coefficients are shifted to the right by 2 in this illustration. So 5 was initially at the first index, now it goes to the third one, shifted by 2. 8 is in the second index, then it goes in the fourth. 3 was in the third index. When we shift it, it goes to the fifth index. Then in the end, at the end of this ciphertext, and at the nth slot, or index, we call that slot also, when we are going to shift it by 2, it's going to go to the second spot because it's kind of wraps out to the beginning. So 1 goes to the second index and 2 goes to the first index. So we shift it 1 and again 1, it goes to the beginning and come here. So this is the rotation or shifting by 2 to the right. We can do the same if we shift it to the left. Well, these are the preliminaries, and now let's see the system architecture and participants. As we already explained at the beginning, we have a server which has an already trained Naïve Bayes model, and we have a client which has a query that the client wishes to classify using the service model, and having in mind the security and privacy goals that we explained in the beginning. In order to do this, we're going to see a few of secure building blocks, starting with secure products of blocks of slots. So this is our first algorithm. It's as an input, we are going to have an input ciphertext, and we have n, which is the size of blocks of slots, starting from slot 0. Basically, n tells us, or nc, how many, the product of how many slots we want to find. In the end, the output, the result will contain the product of each block of n slots at the beginning or the first slot of the corresponding block. It's illustrated, the algorithm is illustrated better with this figure. So basically, this is our input ciphertext. We have A1, A2, A3, A4, etc. till AN. And now this original input ciphertext is shifted to the left by 1. and we get this one. So A2 comes here to the first slot, A3 goes to the second slot, A4 goes to the third slot, and so on. After we shift the original ciphertext, we just multiply the original ciphertext with the shifted one, and this is what we get. A1 multiplied by A2 in this position, A3 multiplied by A4 in this position, so on. Now, this resulting ciphertext is going to be shifted to the left by 2. So basically, A3, A4 is shifted to the left by 2, comes here, and this is done with all other slots. And we multiply it using SIMD fashion that in the way that we are already explained. So A1 multiplied by A2 is going to be multiplied by A3 multiplied by A4. So here we have basically the multiplication or the product of the first 4 slots, later on of the second 4 slots, and so on. Then we shift it to the left by 4 and multiply to the left by 8 and multiply to the left by 16 and so on. In the end, we're going to shift it for log n to the left, and we're going to multiply. So basically, in the first slot, what we're going to have, we're going to see the product of the first n slots. So in the 0 slot, or the first slot over here, we're going to find the products of the first n slots. In the n plus 1 slot, we're going to find the product of the second n slots, and so on. So this is secure product of blocks. Basically, we do it with log n rotations and multiplications. Secure comparison, basically, we have party A, which has integers encrypted using party's 1 public key, while party 2 has the secret key, which can decrypt the ciphertext. What's going to be the result? If for the result is greater than 0, then A is going to be greater than B. Otherwise, A is smaller than B. It's better illustrated with this figure. So this is my A and B ciphertext. So this is my A ciphertext. Here I have my B ciphertext, and we have encrypted here multiple integers in the way that we have already explained. And we want to see for each index or component, which one in index or component wise is greater than the other. How do we do it? Well, we just subtract A with B and then multiply it with R, where R, all of those R's, this is the ciphertext R, and all of those its coefficients are positive numbers. So A minus B multiplied by a positive number, because we want to hide the difference between A and B. If in the corresponding resulting index, if the corresponding index or slot is greater than 0, that means that A of that index of the ciphertext A is greater than B. Otherwise, if any term over here is greater than B, let's say if the second term is smaller than 0, that means that this B is greater than A, because if B is greater than A, when I'm going to subtract A and B, I'm going to get negative number. If I multiply the negative number with a positive number, I'm going to get a negative number. Similarly, if in the first slot, if this A and 1 is greater than B and 1, if I'm going to subtract those, it's going to be positive number. Well, positive number multiplied by positive number is going to be positive. So this is how I do my secure comparison. Now I want to find the maximum of C numbers. Namely, we have a scenario in our algorithm, which has an N2 party. So basically, this is again a secure 2-party computation. So party A has an array of C integers. They are encrypted using party 2's public key. So here it should be party's 2 public key. And party 2 has the secret key. So basically, party 2 can decrypt what party 1 has in encrypted form. Okay, so party 1 has encrypted C integers using party's 2 public key. Thus, only party 2 can decrypt them. And in the end, we want party 1 to find the index of the maximum integer in array. So we have C integers, and the first integer is index 1, second one is index 2, index 3, etc. I don't want to find their value. I just want to know which is the maximum index and nothing else. So how am I going to do that? By the way, in this case, in one ciphertext, I have only one integer and not multiple integers. Okay, that's why I have an array of C integers. Okay, that means one integer is in one ciphertext, another one is another one, etc. We have C arrays. What I'm going to do, I'm going to permute the places of those arrays And then I'm going to apply secure comparison protocol in the way that we already explained. Okay, so I'm going to just subtract them and multiply them with random r. Okay, and I'm going to do it for all of those C integers. Basically, I'm going to compare each encrypted integer with each one, but I'm going to do the comparison after I permute their places in the regional array. So this is after party 1 does those comparisons, it sends comparisons to party 2. Now party 2 is going to receive C multiplied by C minus 1 divided by 2 comparisons, because in order to compare with each other C integers, we need this much comparison. And then it's going to find the 1, but hey, we have the comparisons of the permuted places. So party 2 is going to find the index, which is going to have the comparisons all 0 with the others. Because remember, if a certain number is greater, then if the comparison, secure comparison, is greater, that means that A is greater than B. If a certain number is going to have all of its comparisons positive numbers, that means that it's the maximum. So what we're going to do, party 2 basically is going to find the permuted index of the maximum of the permuted ciphertext, and is going to put 0, is going to encrypt a 0 if it's not the maximum, and it's going to encrypt 1 if it's the maximum. So basically it's going to kind of encrypt C ciphertext, where C minus 1 are encryptions of 0, and 1 ciphertext is an encryption of 1. And it's going to send all of those sigmas, sigma 1 through sigma C, to party 1. Now party 1 is going to do the following. It's going to multiply basically the inverse of the indexes multiplied with the corresponding sigma I, and send this V to A, okay, where this P to the power of minus 1 I is the inverse of the permutations that we did. And send this to party 2, and basically at the end, party 2 is just going to decrypt this, and it's going to find not the maximum integer, but the index of the maximum integer in this input before we did the permutations. And this is what we want. Okay, so how are we going to use all of those secure building blocks for the Naïve Bayes classification? Here is given the pseudocode where we have a server and client. So the server has a trained model. We're going to see how the trained model looks like, a trained model according to Naïve Bayes. And the client has the secret key or decryption key. In the end, that's the output. We're going to have the final classification, which is going to be obtained by the client. And it's going to be the label of one of those C classes from the set of classes. So how does the trained model look like? Well, here we show the portion of the trained model belonging to class CK, and of course this is the same for all of the others. And the first lot of the ciphertext belonging to CK, we just put the class probabilities preceded by all of the feature probabilities of all of the feature values in order. So from feature 1, feature 2, feature F, and in feature 1 we put value 1, feature 1, value 2, feature 2, etc. till the end, and we do this with all of the other features in order. Now, how does a query vector from the client looks like? Where you remember the X vector, X is equal to X1, X2, etc., which had F entries. Well, at the first slot, which belongs to the class probability, we put 1 always. Then, for the feature 1, which is basically X1 from our query vector, if the X1 belongs to a certain value, we're going to have 1 in that slot, and everything else is going to be 0. So basically, X1 is element of F1. That means that X1 is a certain value that's exactly one value that is in this class F1, and we are going to put in that particular slot 1, everything else 0. We're going to do the same for all the other F features. So this is my query vector, and I'm going to multiply the query vector. So on On the server side, we have C ciphertexts, which look like this, from C1, C2, up until CC. The client is going to construct a query vector, which looks like this, and it's going to send it to the server. Then the server is going to multiply them. But hey, when I'm going to multiply them, I'm going to have zeros eventually. And you remember the Naïve Bayes classification formula? I need to find the secure product of blocks. But here, if I multiply 0 by a certain probability, I'm going to have 0. And if I want to find all of those block products of all of those dots, eventually going to be 0. That's why, besides the query vector, I'm going to need what? The inverse query vector, which is the same as the query vector. Just we have, the number of, we have for the feature slots, we have inverted, flipped basically, zeros and ones. So basically, here initially, so this is the inverse query vector. So when I'm going to multiply query vector with the trained model, this is what I'm going to get. But here I have those zeros, and I want to find the probabilities of all, I want to find the product of all of those slots, because this is what Naïve Bayes formula says. But here I have zeros, and I want to remove those zeros. What I'm going to do? Well, the inverse query vector has in those 0 places ones. Okay, so if in the original query vector a certain slot has 0, it's going to be 1 in the inverse query. If it's 1, it's going to be 0. So this was 0 in the original query vector, but the inverse query vector is going to be 1, and so on for all of the features. The only difference is that for the class probability, actually here it should be also 0. So basically I just flip the bits of the query vector. Wherever I had 0, I'm going to put 1, and vice versa. So the client constructs both the query vector and inverse query vector and sends them to the server, and server is firstly going to multiply the query vector with the trained model. Here I'm just showing the portion for class CK. And after that multiplication, it's going to add the inverse query feature vector, and basically the pseudocode is given over here. Okay, so first I multiply the class CK for all of the classes from 1 to C. I'm going to multiply the query vector with the class vector CK. Then I'm going to add it with the inverse query vector. And finally, for this result, I'm going to find the probability of this query to belong to class CK, where K is the index that we use to go through 1 to C. And we are going to use, if you remember, the secure product of blocks product that we explained a while ago. So we're going to kind of execute this loop for C times for each of the classes, and we are going to find basically the probability or posterior probability of the query vector to belong to certain class CK. Now, what we have on the server side, we have an encryption of C integers, an array of C integers, while the client has the decryption key. So basically, we're just going to run the secure maximum protocol that we explained a while ago. So in a way that server is party 1 and client is party 2. And in the end of this protocol, if you remember, party 2 is going to obtain the final classification and nothing else. Well, this is it. In order to compare our results with the state of the art and related schemes, we used a benchmark data set, and usually most of them used Wisconsin breast cancer data set, which has 9 features. Each feature has 10 values, so basically F is 9, and the values at each feature set is 10. So we have 10 elements, and we have 2 classes, cancer and non-cancer. For some homomorphic encryption purposes, we use the Microsoft Seal library. And we used a machine which runs on Windows 10 operating system, Intel i5 processor of 2.4 gigahertz and 4 gigabytes of RAM. And these are our experimental results. Basically, there was no loss of accuracy, among other characteristics. Here we compare some security and efficiency characteristics, namely We have multiple schemes over here, including ours. We compare ours with other schemes in terms of the secure maximum and secure comparison protocol. And for both of them, we see whether there is a certain leakage or not and how many rounds we need for them. And you see our schemes is among the best, outperforms them in terms of that there is no leakage, neither for the secure maximum nor secure comparison, and we do it with less number of rounds than the state of the art. As for the computation and communication costs, they are given here. Basically, our scheme also outperforms the state of the art and related schemes in terms of private and secure Naïve Bayes classification in both computation and communication costs. And yeah, so basically in this paper, we proposed efficient, flexible, and secure building blocks, which can be adopted in other scenarios, not only for Naïve Bayes, of course. We proposed on top of our secure building blocks, privacy-preserving Naïve Bayes, which gives better computation and communication results and efficiencies than the state of the art. And basically all of the privacy preserving goals I kept, and this is more than enough for practical usage. That's all, and thank you for your attention. Looking forward to your questions.